Excellent. So, Jingyan is a research fellow at TTI and a violinist with the Chicago Symphony Orchestra. I just learned.
It's a metropolitan. It's
Metropolitan.
not the one that you buy tickets to go to.
The other Chicago Symphony Orchestra. So that's even better. You can go here play without buying tickets. You should send us announcements about your concert. Okay, so today she's not going to play the violin. Maybe this morning at least she's not going to play the violin, but she will tell us about A/B testing. Jingyan has been at TTIC for a year and a half now, and working on, I'd say, evaluation of humans and machines and the interaction.
That's pretty accurate.
Okay, thank you.
Yeah, thanks, Nati, for the introduction. I'm happy to talk about my work today on evaluating recommendation algorithms through A/B testing. This is joint work with Shoning Lee. She's from Chicago Booth and also in the audience. Feel free to say hi during the lunch, and she can be found by her photo. I think she looks the same as the photo. And also Jingyan Wang from UT Dallas. Before diving into the paper, I want to give a brief overview of my research and contextualize this paper I'm going to talk about within this bigger picture. For my research, I work on developing methodology of evaluation. And the key question is to think about how to model, collect, and aggregate human evaluation data and make decisions. In the past, I worked quite a bit on methodology for evaluating people and human work. For example, in grading, we want to give scores to students' homework or essays. In peer review, we want to decide whether to accept or reject a paper, and we want to select winners in competitions, etc. In these applications, I think about how people behave when they provide their evaluation and rating data. For example, people are miscalibrated, people have different types of biases, and people's behavior might change over time. And I talked about some of these works last year in this talk series. More recently, I get interested in a second type of evaluation problem that I call interactive systems. So some examples are, we want to evaluate how a language model is doing. So a human evaluator goes to have a conversation with a chatbot. And the second example is recommendation systems, where, again, the user sees the feed that's being recommended by the algorithm. And the algorithm learns from human preferences, and we want to see how effectively this recommendation system learns. And here, these interactive settings, I wanted to say, are different from the static settings because here we are exactly evaluating the interaction versus think about grading homework, which I call static evaluation, where the student completes and hands in their homework. The homework is presented to you, and there is not the same type of interaction per se. So I wanted to argue because of this interaction, these problems have more complexities, and we can ask a similar question of how can we evaluate these interactive systems correctly and efficiently. For today, I will talk about one piece of recent work within this interactive regime. We'll think about recommendation systems in particular, and I will talk about addressing one particular challenge that's caused by data feedback loops. And this refers to the phenomena that because these algorithms are interactive in nature, they collect data from the people during this interaction, and this data is used to keep training these algorithms adaptively. And that causes new challenges that we want to address. So now let's go to this work. We'll look at this problem through the lens of causal inference and experimentation. So I'll give a brief overview on that. I'll introduce the problem we are addressing, which is called symbiosis bias. I'll describe our formulation using multi-arm bandits, and we'll describe our theoretical results. And let's start with the background. So recommendation algorithms, they appear almost everywhere on online platforms. For example, think about social media, online marketplaces, freelancing labor market, etc. So now think about yourself as a manager at one of these companies. Your company runs a default algorithm that's already in place. Now your engineers, they've been working really hard, and they say, oh, we discovered it's more effective to recommend more recent content to the users. So we make these changes and we propose this new algorithm that we call algorithm 1. So as the manager, the question you want to answer is which algorithm is better. And if the new algorithm is better, we deploy the new algorithm, and otherwise we don't. And this type of question is often addressed through the framework of randomized control trials, or also called A/B testing. So what does a randomized control trial do? We have users, and in this experiment, we assign users uniformly at random to the control and treatment group. So we call the original algorithm the default one as the control and the new one as the treatment. We compare the performance between the users that are assigned to the two groups. And that helps us to determine which one's better. These experiments are widely adopted. So large companies, they run thousands of experiments every week on millions of users, and that has a large impact in terms of the revenue, user experience, etc. Here, I talk about experiments, about running experiments for recommendation algorithms, but these experiments are more general, and we can consider other problems. For example, how do we run algorithms and compare pricing algorithms, healthcare intervention policies, or even language models, etc. And we hope the results and the insights that I'll talk about later also apply to these other settings as well. Although we'll stick with the recommendation algorithm application for the talk. So now let's put this randomized control trial under a causal inference language. There is some metric, we call it Y, that we're interested in measuring. For example, this can be user engagement, click-through rate, or whether the user purchases a product or not, etc. Our goal is to estimate what's called the global treatment effect, or the GTE, which is the difference in terms of this metric if everyone were assigned to the treatment algorithm, minus if everyone were assigned to the control algorithm. And a simple and commonly used estimator is just to take the empirical difference between users in the treatment group minus the users in the control group. And this is called GTE hat, which stands for the empirical when there are n users in each group. In an idealized world, because the assignment is uniformly at random, and by the law of large numbers, we hope this empirical estimate GTE hat to converge to the true GTE. And this will give us the correct comparison where when the GTE is greater than 0, that means the treatment algorithm is better. And if the GTE is negative, it means the control algorithm is better. However, a common problem that people have been addressing in the literature is exactly this phenomenon where the limit of this empirical mean does not converge to the true GTE. And let's say this converges to something that we call GTE tilde, that is not equal to the true GTE. Why does this happen? And this is usually due to what's called interference, which says there exists dependence between users in the treatment and control groups. So let's quickly discuss a few examples about why this interference happens. One example is called network effects, which is the fact that the control users and the treatment users, they might talk to each other, and that causes this dependence. For example, when we recommend more recent content to users in the treatment group, these people might have friends in the control group, so they tell their friends in the control group about what they see from the recommendation systems. And once the control group hear about these news from the users in the treatment group or their friends in the treatment group, it's possible that they are more likely to click on the ads in their version of the recommendation algorithm because now they already hear it from their friends. They are intrigued. They really want to know more details. Yes.
So I assume that every time a user appears as an encounter, you're flipping a coin, right?
Yes.
So that coin is presumably not biased.
Sure, we can.
So even
yes.
if the distribution is drifting over time, you're still getting the same distribution at any moment in time.
What is the distribution?
I think the issue is different. Like the issue is that you're trying to estimate how well will the system work when you just have algorithm 1. But maybe algorithm 1 only works if some users are, if my friends are algorithm 0 and I'm algorithm 1, then it works. But if algorithm 1 is on its own, it's not going to work.
Okay. I can see there's an issue there.
Okay, that's I think the issue here.
Yeah, so the other common example people talk about is with vaccines. So let's say we want to study the effectiveness of this particular vaccine. We divide people into 2 groups. We give people in the treatment group the vaccine. And we measure a difference, which might be different from the difference if everyone gets a vaccine. Because whether you get infected depends on whether other people around you have the vaccine or not. Oh, and going back to the example, it's also possible that users in the control group are less likely to click because they've already heard it from their friends and there's no point to look at this news again. So that produces bias in terms of the estimate of the treatment effect. A second example is inventory constraints. For example, now let's think about the intervention as recommending new products. And now users in the treatment, this product is very popular. The users in the treatment group, they all buy this product, so this product runs out of stock. Now people in the control group can no longer buy this product. And that also affects the treatment effect estimate as well. The third one, which, Matt?
Sorry, I was just wondering, how would you ever know when this happens in practice? You never know GTE. That you're not converging to GTE.
Yeah, so one thing we can do is we first ask, a common procedure is we estimate the GTE from the experiment. We determine this is good because we see a positive GTE. So now we roll out the product and start deploying the new one. But then we see now once we roll it out, everyone is in the control, is in the treatment group. Mm-hmm. This doesn't work out as the GTE we measured, and that's when people look at is this an issue with the experiment or where is the issue? But that's a good question. And now the third type is caused by data feedback loops, which says the treatment and control algorithms, they share user data, and that also creates bias. And this is what we'll be talking about next. What is data feedback loops, and why does this cause a problem? So data feedback loops what's called symbiosis bias, and let's look at what this is about. The effect or symbiosis bias of feedback loops is confirmed empirically by an experiment that's done at Google. So here we have the same example where the intervention is to recommend more recent content to the users. So it's not a surprise that users in the treatment group, they start engaging more with the recent content because that's what the intervention is. However, the more interesting observation is now the users in the control group, their algorithm does not change, but they also start engaging more with the recent content. So why does this happen? And this is the interference we talk about. In this paper, they give the following reason. So we have 2 recommendation algorithms. They are trained on some data in terms of the user preferences and user behavior. As this experiment keeps going, we collect more human data from users in this experiment in terms of their clicks, their likes, purchases, etc. This data goes back to the database that trains both algorithms adaptively. And because of this data feedback loop creates dependence between users in the treatment and control groups, and explains this phenomenon where we collect data from users in the treatment group to learn that more recent content is effective. the control algorithm now is also able to learn from this data and now starts recommending more recent content to the users and causes this observation that's being made. Right, so as we talked about, users in the treatment group, they contributed data to the database that in turn trains the control algorithm as well. And this creates interference due to this data sharing that's also called symbiosis bias in the literature. So I think this name is kind of self-explanatory. It says both algorithms, they live on the same data in the symbiotic way, and hence this name. And hence, symbiosis bias may cause the GTE to be not equal to the true GTE estimate to be unequal to the true GTE. In this work, we come from the motivation that in this particular example, we often care more about decision making in terms of deciding which out of the two algorithms is better, rather than measuring the treatment effect effectively. Like as a manager, I primarily want to know which algorithm is better and whether an algorithm gives a 36 or 37.5 improvement, that's less important in terms of which algorithm to deploy. Because the answer is pretty quick, yes.
Just a quick clarification question. Do you assume the same data set for training and inference, or are they going to be different?
I wanted to say the same data.
I see.
And like there isn't really inference. Well, the inference is done by just taking the empirical means, so we don't consider more sophisticated inference procedures. That's sort of fixed. Like, it's pretty intuitive and also simple to consider the difference in means estimators, so we fix that part.
So would it be better to think of this, so you're getting data, the data is going into a shared database.
Yes.
There's a symbiotic effect. Would it be easier to model this as a kind of online learning, where you're like an online learning, you get to see all the. There's no real distinction between training and test.
Yes, I agree with that, and that's what I think we'll be doing next. So let me know, like once we talk about the model, if you have more comments or questions. Yeah. Right, and because we care more about decision making. Our question is, although we know symbiosis bias causes the estimate GTE tilde to be not equal to the true GTE, do we have the same sign in terms of these two quantities? And if they have the same sign, it means in the experiment we are making the correct comparison. And if they don't have the same sign, it means we are making the wrong comparison in the experiment. So that concludes the introduction of experiments and also symbiosis bias. Are there more questions on that before I talk about the mathematical formulation? All right, so now let's talk about how we think about this problem through a formulation in terms of multi-arm bandits. Let's quickly review the standard stochastic multi-arm bandit setting. So here we have k arms. Each arm is associated with a distribution d1 through dk. And each distribution, for simplicity, let's assume it has a standard normal noise with means mu1 through mu k. And also, with a lot of generality, let's assume mu1 is the highest, although like all the means are unknown, and we don't know but mu1 is the highest. A bandit algorithm does the following. It runs over iterations from 1 to this horizon big T. In each iteration, it decides to pull an arm I out of the k arms. It collects one sample x from the arm that's being chosen. And then this algorithm keeps a history of the arms that have been pulled so far and the samples collected from these arms. And from this history, the algorithm decides which arm to pull in the next iteration. In a standard bandit problem, a common metric to look at is the regret, which is a difference between the maximum possible regret, which is to pull arm 1 all the t times, minus the actual reward that's collected, which is the sum of x in expectation. And the lower regret, the better. So now let's frame this experiment under this Bandit framework. So now we have two algorithms, A0 and A1, the control and the treatment. They separately decide to pull an arm, I and J. They separately collect a sample from the arm they choose, and the samples are called X and Y. So now they put the two samples in the same history, and this the two algorithms decide which arm to pull based on this shared history. So that's the setting we have to model this randomized control trial with data sharing. Yes, Matt.
Sorry, you said the control and the treatment are the algorithms, not the bandits, not the arms. Sorry, not the arms, right?
Yes, they are. We want to know if algorithm 1 or algorithm 0 is better. And that's a distinction from some of the other works in causal inference. So people also study, well, maybe this is a little, people also study if we want to know a treatment effect in terms of the difference between two arms, then how do we do it? But that's not what we do. Yeah. All right, so this algorithm box says exactly the same thing as the previous figure, but let's just formalize it and quickly go over it again. For iteration from 1 through big T, we have two algorithms, algorithm 0 and algorithm 1. They separately select arms Nij. They separately collect samples X and Y from their chosen arm. They add the two samples to the same history, and based on this shared history, they decide separately which arm to pull next. With this algorithm, what we are able to measure is this new regret definition. This is a regret of algorithm 0, which is similarly defined as the maximum possible regret, minus the regret collected by algorithm 0, which is the sum of X in expectation. However, it is important to see that this regret is different from the regret if algorithm 0 were running by itself. And this is because this regret also depends on algorithm 1, because algorithm 1 contributes to the history, and that affects which arm algorithm 0 decides to pull next. And therefore, we use this notation 0 bar 01 to emphasize that the regret of algorithm 0 now depends on algorithm 1. And likewise, we define the regret of algorithm 1, which also depends on both algorithms 0 and 1 in this setting with data sharing. And this is an important difference that this regret tilde is different from the regret in isolation. Are there questions about that? Or is it clear? Okay, cool. Right, so now to reframe our research question within this Bandit framework, we are interested in comparing two algorithms in terms of measuring the GTE, which is the difference in terms of the performance of the two algorithms, that's regret 1 minus regret 0. In the experiment, we are able to measure this GTE tilde that's defined based on the regrets measured under data sharing. We are interested in looking at whether these two quantities have the same sign or not, which implies the decision, the comparison we are making from the experiment is correct or not. So that concludes the formulation. Are there questions about the Bandit formulation for this problem? David?
When you do the true GTE,
Yes.
That GTE, presumably if I adopt algorithm 1, I can't remember which one's the new one. If I adopt the new algorithm,
Yes.
it's going to change the data, the history.
Yes.
So its return is going to be drifting over time. Its performance is going to be
Yes.
drifting over time,
Yes.
right? So I'm wondering if this definition of the GTE, of the true GTE, is taking that into account.
I think so. So GTE is a cumulative regret over time.
Right, but
Right.
it's online and
Yes. So we are
and
interested.
You're learning as you go.
Yes.
Both algorithms are learning as
That's
they go.
correct. Yes. I think that's kind of exactly the highlight we want to emphasize. Like looking at the dynamics of algorithm 1 compared to the learning dynamics of algorithm 0. That's what we are looking at.
And their joint dynamics are different from either running
Exactly.
independently.
Yes.
I'm a bit confused. I mean, ultimately, you want to ask whether you should replace algorithm 0 with algorithm 1. Right? So, but you could directly measure. You don't have to do this conditioning. I mean, you don't algorithm. When you test algorithm 1, you can test it without the other information from algorithm 0. So why give algorithm 1 when during testing the added information from algorithm 0?
So I suppose Nati's question is like, why do we do experiments? Kind of like,
Well,
why
do
don't we
the
just
testing?
measure regret
Why
1,
do
regret
you
0?
do why do you do the testing this way?
I think this is a standard practice for companies. I think this is also like, well, like this is both like safer, also more seamless. Safer in the sense that like if the algorithm doesn't really work, then like we are deploying this to like millions of users, and that has like larger impacts versus we first allocate 0.1% of the users to the treatment group, and now it helps us look at the effects within a smaller regime.
No, I'm not asking why
Yes.
do A/B testing.
Yes.
I'm
No, I
completely
missed the
resistant to the A/B
question.
testing.
Yeah.
But when you do A/B testing, you can choose to give algorithm 1 information gained by algorithm 0 or not give it that information. So
I see.
why did it seem? So what I'm asking is, if you really want to analyze, do A/B testing to see how algorithm 1 behaves without that information, because that's how actually you can deploy it. Why during the testing are you giving it that information?
I think this is mostly due to like engineering efforts. Like now, to properly run experiment, we need to like isolate the data, sanitize the data in this way, so that the data does not cross this line between treatment and control. I think that's the proposal.
And perhaps a complicating issue is that the same person is going to be visiting the system repeatedly.
Yes.
And my assumption is you're flipping different coins every time they come.
No, usually randomize the users. I mean, if you have any notion of user record, which you usually do, you randomize the users, not the yeah.
So then it does seem possible.
But probably they share some like previous training, like general pipeline.
I mean,
Yeah, I think this is mostly due to engineering effort. And I guess the other point is like nowadays companies are doing this without adding this extra engineering thing. And if the results are the same anyways, then why bother? Like, which is part of the analysis. Like, are the signs really the same, or like are there cases where the signs are different?
Maybe you can learn faster if you have the data of the other algorithm, right? Maybe you can improve, like you understand faster whether that new algorithm works better. Maybe
That's true as well. Like
well,
if
that's what we'll see, but yeah.
if one algorithm is like if the treatment only has like 0.01% of the users, then like not surprisingly that algorithm learns slower, and if there's a way to do the experiment with shared data, that's more efficient as well. Yes.
I just want to try to understand a little bit about the current literature on the even simpler problem. So let's say if you don't have two algorithms or two data sets, just one algorithm collected that is used to collect one data set for both training and evaluation. That also will introduce some bias, right? And also in the offline RL literature, you would typically we don't assume stationary target policy, right? The target policy could be an online valid algorithm, right? So I'm just curious, like, what if you directly just apply some offline RL approach, and what would the bias be? And in this simpler setting, like, what's the current solution in the literature?
So for the first part, like about training and testing, I think in our particular problem, we don't really separate it into the training and testing.
So like you're using the same
learn
data set,
online.
right? So that creates some bias as well, right? So is there any discussion in the literature for this even simpler problem?
So you are thinking about like for a problem where there are separate training and testing phases, and the two algorithms we are comparing, they share the same training data. Is that the type of problems?
Yeah, so maybe let's go to the second question. So like, let's see, I just want to apply some offline RL approach. So often the setting is that you have a behavior policy, you know the sampling probability of the behavior policy, and then you have a target policy. The target policy here does not have to be stationary, right? It can be any possible online learning algorithm. So what if I just apply this? Would that give us an unbiased estimator in the setting? And so this is a special case because your behavior policy is exactly the same as your target policy, right?
But you're talking online, so you're talking about regrets.
Yeah, so
So I guess it's not comparing two policies. Here we are considering two algorithms.
right.
And the algorithms are like learning along the way.
Right, so in offline RL setting, the target policy could also be a non-Markovian policy, which includes online algorithms.
I think I'm interested in the proposal. I didn't fully get it.
Maybe you continue with your talk and
Okay,
Oh, yeah,
we'll take
maybe
it
we can
offline.
discuss it offline. Alright, cool. So now we'll go to our results. To introduce the results, we'll first introduce a few very standard Bandit algorithms so that we are on the same page. One algorithm is a greedy algorithm, where the algorithm selects the arm with the highest empirical mean in each iteration. Because this algorithm is greedy, it doesn't explore, it incurs a bad regret, which is linear in T. Absolute greedy adds exploration on top of the greedy algorithm. Where in exploration, if a step is an exploration step, samples are armed uniformly at random, and if we tune this probability correctly as in the order of inverse of T, this algorithm is optimal and gives us optimal log T regret. And likewise for the UCP algorithm, it's also optimal, and in each iteration it selects the arm with the highest empirical mean added by this confidence bound. Let's start with a simulation setting. So here we are first plotting the regret separately if epsilon greedy were running by itself and if greedy were running by itself. We see greedy is a straight line, it has a linear regret which is much higher than epsilon greedy, so this makes sense. And we know this from standard theory. And now let's run these two algorithms together under data sharing and plot the regret that we measure, the regret tilde. We see that the regret of both algorithms improve, so they both of them decrease. For the epsilon greedy algorithm, it becomes a solid dark blue line. And for the greedy algorithm, it's a solid red line, which now is significantly lower than the original regret if greedy were running by itself. And now, within this experiment, we conclude that greedy is better than epsilon greedy, because the red solid is below the blue solid. But that's actually the wrong comparison. If we were running an algorithm in isolation, greedy, which is the dashed light red, is worse or higher than the dashed blue, which is for epsilon greedy running in isolation.
What's the data set?
This is just a simulation for standard.
It's synthetic data.
Yes. So, why does this happen? First of all, why does greedy incurs a high regret when it runs by itself? And this is because if the first few samples of the optimal arm happens to be low, because greedy doesn't explore, it determines that this arm is bad. And it gets stuck in pulling some suboptimal arm. And whenever this case happens, greedy incurs a linear regret. That's where the linear regret comes from. So now when we run the greedy algorithm jointly with epsilon greedy, greedy algorithm no longer gets stuck because whenever this happens, epsilon greedy will collect more samples from this arm. And greedy algorithm will be like, oh, now I see more samples that are collected by someone else. I realize this arm is actually pretty good. So intuitively, under the data sharing setting, greedy is free-riding the exploration that's done by the other algorithm, which is epsilon greedy in this simulation. We formalize this intuition and provide a general theoretical result. Here we consider running greedy jointly with another algorithm A, And this general class of algorithm A satisfies 3 conditions. The first one says we assume the algorithm A is anytime. This is more for technical convenience. Don't worry about the first condition. The second condition says its regret rate of algorithm A is now hurt by the extra data that's shared by greedy algorithm. So intuitively, if an algorithm has more data, it performs at least as well. The third one says this algorithm A pulls the best arm at least log t times with high probability. With the specific condition, let's not worry about the exact details. Roughly, it says the probability of the algorithm pulling the optimal arm, the probability that this is smaller than log t is very small. And this is also a mild condition because if algorithm A is sublinear, it pulls the best arm a linear number of times, but we only require log t, which is much smaller. And if algorithm A satisfies these 3 conditions, then when we run greedy jointly with this algorithm A, the regret incurred by greedy under data sharing is bounded by a constant. And now, if we think about the algorithm A as any sublinear algorithm, we know greedy incurs a linear regret when it runs individually. So in reality, algorithm A is better because it incurs a lower regret. But now, with this result, under data sharing, greedy incurs only a constant regret. And we know from condition 2 that the algorithm stays linear under data sharing. So under the experiment, from data sharing, we determine that greedy is better, which is the wrong conclusion for the comparison. I argue that these 3 conditions are pretty mild, and we show that the general algorithm, the common algorithm of epsilon greedy and UCB, they satisfy these 3 conditions. So that's the result. I feel a little ambitious, so let's spend 10-ish minutes talking a little bit about the proof. Because, yes.
But I missed the point. Like, if you come to the wrong conclusion, meaning on the one hand you need to switch to greedy, but it doesn't make sense. So what's the point of, like, what's the conclusion?
I think the conclusion is if a company is running a standard A/B testing experiment, then what you learn from the experiment is incorrect. So you really need to be careful about how to design
don't do data sharing. Yes. Don't do data sharing. That's what it means.
Yeah. So maybe you can think about like hire like a team of engineers to implement this more complicated setting. So that's yes. Actually, we also have results where the science is same, and I think that's also relevant. Or in certain cases, like it's the same thing. All right. So we'll talk a little bit about the proof. Initially, we find this proof like both interesting and challenging because typically in the Bandit literature, we typically prove regret that's in the order of log t. And if that's the target rate, then oftentimes we assume any suboptimal arm k has already been pulled log t times in the analysis, and we show that it's not pulled many more additional times. And if we already assume that each arm is already pulled log t times, the empirical mean of the arm concentrates nicely, and that really helps with the analysis. However, we can't do this because we want a constant regret for the greedy. We want to analyze what happens before the empirical means of the arms concentrate, and that brings the challenge. So we carefully decompose and track the number of pulls for each arm in the analysis. We'll talk about the proof. I promise you that the proof will end, and we'll talk a little bit more about other interesting stuff after the proof. So a little bit notation. Let's use nk of t to denote the number of total samples for arm k pulled jointly by both algorithms up to time t. So the number is in between 1 to 2t because there are 2 algorithms supplying the samples. we use the notation mu k of t to denote the mean of arm k at time step t, and mu k of s to denote the mean where there are s samples on arm k. So these two are different. One is I time t, the other is when there are s samples. We use I to indicate the arm that's selected by the greedy algorithm at time step t. And this difference between mu1 and mu k is often called gap in the literature, which we use delta t to denote. So here we bound the number of poles by the greedy algorithm, and we want to show this is a constant. So when does this happen? This happens when greedy pulls arm k, which by definition means the empirical mean of arm k is higher than the empirical mean of arm 1. That's why greedy pulls this arm. And we decompose this event into two cases, where the first case is when the empirical mean of arm 1 doesn't concentrate, and the second event is when the empirical mean of arm k doesn't concentrate. So pictorially, if a mu1 bar is lower than mu k bar, then either mu1 bar is below this midpoint, or mu k bar is above this midpoint. So now let's look at the two terms separately. For the first term, we are concerned with when the empirical mean of arm 1 doesn't concentrate. We look at this probability term inside the summation of t, and we take a union bound where we think about the number of samples at this time step t, t being anything in between 1 to 2t. And we further decompose the summation to first look at s goes from 1 to tau, when the number of samples is small, and from tau to 2t when the number of samples is large, where tau is on the order of log t. For the second term, we apply Hofting, and if you trust me, this gives us a 1 over t squared order. For the first term, it's bounded by tau times the probability of the total number of samples smaller than tau, which is where we use the assumption. We'll plug in the value of tau, and this is what we see from condition 3 of the theoretical result. We assume in condition 3 that this is of order 1 divided by t to the order 1.1. And finally, taking the summation of t, this is a constant. So that's for term 1. And here we analyze the empirical mean of arm 1. We apply this condition from the theorem assumption. But this, we only assume it for arm 1. We're like, because arm 1 is an optimal arm, it's safe to say this arm has been pulled many times. And therefore, now we move on to analyze the empirical mean of a suboptimal arm k. We'll need a different analysis, like this doesn't apply to arm k. So for the second term, that concerns the event when the empirical mean of arm k doesn't concentrate, and we take the summation over t. The tricky part is we are taking the summation over t, and like, what if this event happens at a particular time step and we don't get more samples, and this event keeps happening at many time steps, and when we take the sum, that's large. So that's the problem. However, we make this observation that whenever this event inside the probability happens, by definition, greedy pulls arm k, so we get one more sample of this arm k. And therefore, we never get stuck. Whenever this event happens, we get one more sample, and that contributes to the concentration of the arm. So we formalize this intuition. We again take a union bound over the number of samples, that's S, to think about what happens if the total number of samples at this time step t is S. Then we flip the two summation signs and decompose this condition inside the indicator to be two parts. The first part is the first and the third term pulling together, and the second part is from the second term. So now I argue this thing above this blue line, the summation is at most 1, because whenever this condition is satisfied, this means we have S samples at this time step. And we get one more sample, so at any future time step, the number of samples is at least S plus 1. So this event only happens once over time. And therefore, we put the rest of this together from the second term, and now we apply standard Hofting, and if you trust me again, this is also a constant. So for the second part of the analysis, the key is to convert this union bound in terms of the time step t to be a union bound over the number of samples S, which is much easier to keep track of. I think that concludes the proof. Right, so for the first time, we use the assumption that the algorithm posts arm1, the optimal arm, at least log t times. And for the second term, we make this argument where whenever we collect a sample from arm k, it helps with concentration. And this proves this result where if we run greedy and another algorithm A together, the regret incurred by greedy under data sharing is bounded by a constant. So we've seen the greedy algorithm performs very well under data sharing because it's free-writing the exploration done by the other algorithm. However, in practice, hopefully companies are smart and they don't really want to test if the greedy algorithm works or not because it doesn't. So we are more interested in comparing two good algorithms as opposed to greedy. So now we'll look at briefly some results in terms of comparing two linear regret algorithms. To do that, we construct parameterized classes for algorithms where we have this parameter alpha in between 0 and 1 that represents the exploration level. We modify the absolute greedy and UCB algorithm where we slightly change the exploration probability for absolute greedy and also the confidence interval for UCB so that the regret of either algorithm with parameter alpha is t to the alpha when alpha is larger than 0, and it reduces to log t when alpha is 0. So alpha equals 0 reduces to the standard absolute greedy and UCB algorithms with optimal regret. Why do we do this? Because we want to construct a spectrum of algorithms with different performances so we can look at whether the comparison is correct or not in our analysis. So our theorem results says, let's consider two algorithms where parameter alpha 0 is smaller than alpha 1. And we assume alpha 0 has this parameter algorithm 0 has parameter alpha 0, and algorithm 1 has parameter alpha 1. Individually from the previous claim, we know if one algorithm runs individually, the regret is t to the alpha. So this means alpha 0 is better in reality. And we show that under data sharing, the regret of either algorithm stays the same, which means from the experiment, we also conclude alpha 0 is better. So maybe coming back to the questions about like, why don't we just do more engineering work and split the data and isolate the data? This result implies that in certain cases, that would be nice, but that's not strictly needed. And if we run an experiment, we can confidently determine that the result is actually correct, even without doing the extra things. Right, so this result says that the experiment gives a correct comparison under these parameterized classes of epsilon, greedy, and UCB. So to put these two pieces of results.
So can you say that always so the general claim would say that for any two algorithms that has a sublinear regret,
Yes.
maybe under data sharing, you will see the same observation. So here you gave one example.
Yes.
With the greedy, you get the opposite conclusion,
Yes.
but it has a linear regret, so it doesn't really it's not interesting.
Sure, yes.
So maybe if you have reasonable algorithms with sublinear regret, you will come to the right conclusion under data sharing.
Yeah, so that's what we believe. It would be nice to prove this very general result, and we try to demonstrate with two pieces of the parameterized class. Yeah. All right, so to put these two pieces together, the intuition for these two results are as follows. If we run one algorithm in isolation, then the algorithm needs to balance exploration and exploitation, and when it has an optimal trade-off, it incurs a lofty optimal regret. And if it has either too much exploration or too much exploitation, the regret starts being worse. However, if we run an algorithm under data sharing with a sublinear regret algorithm, then exploration becomes the tragedy of the common, and the more this algorithm exploits, the more it takes advantage of the exploration by the other algorithm. So this curve becomes more monotonic, where more exploitation is strictly better, even if something like greedy excessively exploits. Right. So what are the cases when the comparison is wrong? Is when we compare this red point to the blue point, where the red point is higher without data sharing but lower with data sharing. And on the other hand, when the comparison correct, when you compare two blue points on the right side of the curve, because it's both monotonic without or with data sharing, the conclusion is the same. And one question next is how we know like there are two regimes. In reality, we don't really know which regime we are in. So how do we do that? I won't describe the details and we'll conclude shortly. But we'll use ramp-up experiments, and from the experiments, by looking at what's happening in the trace of the experiment, we are able to determine which regime we are in terms of the correct comparison versus the wrong comparison. So zooming out a little bit, one thing that I like about this work is we combine ideas from Bandit algorithms and causal inference. Because we start with this motivation of addressing interference when we evaluate recommendation algorithms, that inspires a new Bandit problem. And in turn, because we are comparing Bandit algorithms, that highlights a dynamic setting in causal inference that's last studied in the past. And zoom out even a little more. This is an example where we try to understand how do we evaluate interactive systems and how are interactive systems different from the static tasks. And I believe there are many interesting open questions under this topic. For example, we can think about how to collect data from people and how to run inference. And because now we have this time element in this interactive processes, we can think about how people's behavior changes over time. And can we change the data collection scheme also over time? Maybe in the beginning, we'll ask the user a lot of coerced questions, and later on we change the scale, and something like that will be possible. And I think there are also questions about, with these more complicated interactive settings, how do we design the experiment? For example, think about language models. If we hire N people to provide their preferences between two models, and they are allowed to have a conversation with answers, and assume we have a fixed budget, which is N times M, like how do we choose these parameters? Do we want to hire more people where each person interacts less with or has a shorter conversation with the model? Or do we want to hire a few people who intensively spend a lot of time to engage with these language models and provide their preferences? And the second example I think about, the second example is from a robot navigation. So here, let's again think about, we compare to navigation algorithms. We can deploy the robot in different settings. Maybe we can intentionally create some obstacles that don't really exist in real life. Like, do we want to do that? Do we not want to do that? How do we select a set of representative environments to evaluate the two navigation algorithms and infer which one is better? And I'm happy to talk about more of these ideas together offline. With that, I'll conclude, and I think we're running out of time, but maybe one question. Yeah.
for a question? We had a fair number of questions during the talk. I just had one thought.
Yes.
Google is running very heavy learning algorithms, I presume, right?
Learning algorithms.
So when we talk about analyzing the historical data to improve the algorithms,
Yes.
right? So that might be very expensive. They might be doing something like retraining a language model. So it might be very hard to isolate two different training processes because their training is expensive.
That's a good point. I agree with that. And maybe like if this combines with like in recommendation systems some image classifiers and that's also trained on data, it's hard to train like a image classification model only from user data from scratch from this particular treatment group. So I agree with the observation.
Okay, we have lunch downstairs. Thanks again.
Don't worry about it. I replied. Okay. Oh yeah.